Right, when we deal with electricity, we use symbols to represent things. So our voltage source, we generally use a short line and a long line. And that is going to represent a battery or any kind of power source like an outlet. And usually you'll write the voltage like 12 volts, 9 volts above the battery so you know. This shorter end is the negative end of the battery or the outlet, and then the longer end is the positive. And because Ben Franklin screwed it up, we for years said that electricity flows in the direction of positive charge. So away from positive toward negative. And that's called the direction of current or conventional current. So that's what we're going to use, is we're going to pretend like electricity flows away from positive and toward negative, even though really it's electrons that flow, and you know that they would go away from negative and towards positive. We'll call this the direction of current. I is going that way. All right, then we have resistors. And whatever the device is in your circuit that's converting energy from usually electricity to heat, it's a resistor. And that will be measured in ohms, which ohms, the symbol looks like a little horseshoe. So maybe we have 3 ohms, that little horseshoe symbol. And then we can get a few more things. This is just a basic wire. So this was a resistor, battery, a wire. You can probably guess that is a switch. And that's what we're going to need to make most of our drawings for circuits. So I'll just take that 12 volt battery and I will put that 3 ohm resistor right there. And then maybe let's put a 2 ohm resistor there. And then a switch. All right, so right now no electricity would be flowing in this circuit. This is called a series circuit because there's one loop to make it around from one side to the other. And it's important to realize when you look at this 12 volts, that is the potential difference between this end of the battery and this end of the battery. This end has much more positive charge than this end, 12 volts worth. But there's no path to get from here to here. If you close the switch, now there's a path. Now electricity starts flowing in the circuit. So how much electricity? Well, it turns out that we're going to encounter 3 ohms and 2 ohms of resistance, which makes a total resistance of 5 ohms. So if we do Ohm's law, I equals V over R, that's the form you're going to see it in a lot. 12 over 5 is 2.4 amps. Both of these resistors are going to get 2.4 amps. This is like having one river, and the current is the same everywhere in the same river. So 2.4 amps is going to be the resistance. Now, if you want to measure the voltage of these devices, they actually get different voltages. This one here, if you do V equals I times R, we say that voltage drops from here to here. It drops by 2.4, that's I, times 3, that's R. So 7.2 volts we lose right there. And we lose some more here. We're going to do V equals I times R again. And so if I have the same amps, 2.4 amps, but now only 2 ohms, I only lose 4.8 volts. Interesting thing that happens, if I lose 7.2 volts here and I lose 4.8 volts here, I've lost all my voltage, all 12 volts, which you would expect because you lose voltage at the resistors. You gain it at a battery, you lose it at a resistor. If you make a complete circle, the voltage is 0 around the circle. So if you went from here, you would gain 12, lose 7.2, lose 4.8, and we're back to 0. So that's how you use Ohm's law. how much power would these things be radiating if they were like, light bulbs or something? How much power? Well, power is amps times volts. So they each have different voltage. So 7.2 volts is this one's voltage. They have the same amps. So 2.4 times 7.2 would get you the power. All right, I have my calculator here now. So I was taking 2.4 amps times 7.2 volts, and that is 17.28 watts, or 17.28 joules per second, all right? And for this one, I have the same 2.4 amps, but I'm multiplying that by 4.8 volts, a little bit less voltage. And I get 11.52 watts. Right, so these wattages are the rate at which these resistors are converting energy from electrical into some other form. Right? It's important that you realize that voltage is across devices. So there's a 7.2 volt drop across this resistor and a 2.4 volt drop across that resistor. Voltage doesn't flow. It's not like voltage leaves the battery. Current leaves the battery. Voltage is across devices. All right, let's analyze this for a parallel circuit. So I've got the circuit drawn. I've picked out three things that I want to plug in. Let's just say it's a regular household circuit, so you have 120 volts. A lot of times when you buy electrical devices, they will say the wattage on them, not the ohms. But we can figure out the ohms if we want to, but the wattage is pretty important. So let's say that our curling iron is 1200 watts, and our hair dryer is 720 watts, and our toaster is 240 watts. And I've got those three plugged in. Well, they're all gonna get 120 volts because if you take any loop, you're gonna just go by one resistor. And that means you're gonna have to lose all 120 volts. So they're all gonna get 120 volts. So if power is amps times volts, you can get all their amps if you want to. This one is gonna have 10 amps because 120 times 10 is gonna get you 1200. This one's gonna have 6 amps because 120 times 6 will get you 720, and this one's gonna have 2 amps because 120 times 2 will get you 240. You can also use that to find their ohms. So 120 divided by what ohms will get you 10 amps? It's gotta be 12 ohms. And here, 120 divided by 20 ohms would get you 6 amps. And then 120 divided by 60 ohms will get you 2 amps. So that's the ohms of the three devices. An interesting thing is when you get to the main part of the circuit, right here, like in my house, these would be called the home runs. They would be going back to the garage, where all the outlets have dumped together. Like these would be each individual outlets that I might have something plugged into. These runs will be going back to the breaker. And in my house, if you get over 15 amps in the bedroom, you're gonna trip the breaker. And then you have to go out and reset it. But let's say you had 20 amp circuit breaker. Would we trip it? 10 amps and 6 amps and 2 amps. When they all dump together, you'd have 18 amps, so you'd still be okay. So this would not trip the breaker. All right, I promised that we would also talk about how much this costs. So we can use an equation, energy is power times time. Oops, energy is power times time to find the cost. Because power is energy over time, so energy times, or power times time should give you energy. We're not gonna use the usual unit for energy, the joule, because it's just way too small for what we're trying to do. So I'm gonna use the power in kilowatts of these three devices. So let's start with the curling iron. It's gonna be 1.2 kilowatts. And I have no idea how long you leave a curling iron plugged in for, but let's say a quarter of an hour, 15 minutes. then it looks like that is going to be somewhere around 0.3 kilowatt hours. 0.3 kilowatt hours. It's not kilowatts per hour, it's kilowatt times hours. This was hours that I multiplied by. So this is the unit of energy, right? A watt second is a joule. A kilowatt hour is much more than that. It's 3,600 times more than a second an hour is, and 1,000 times more than a watt. So it's 1,000 times 3,600. So 3,600,000 joules in a kilowatt hour. It's a big unit of energy, but it's common to need that much energy to run something like a curling iron, and it's not that expensive. It turns out that it's about 13 cents per kilowatt hour. So all I would need to do is take this amount of kilowatt hours that I used, which was 0.3, and multiply that by 13 cents. And you can see that I did not use very much money here. About like 4 cents worth or something. 5 cents maybe. So for each of these devices, the 720 watts, let's say that I have the hair dryer running for an hour because I got a lot of hair to dry. Then I would use 720 watt hours or 0.72 kilowatt hours, and then I would multiply that by 13 cents. So that's how you find the cost of electricity.